Hello everyone and welcome to today's lecture video, which is on Stirling's formula, which I've already derived using the Euler-Maclaurin summation formula, but in today's video I'm going to offer a second derivation by a different method, namely Laplace's method. And this method is going to really make explicit why the factor radical 2 pi n appears in Stirling's formula. And so in today's video, we're going to derive, again, Stirling's formula, which says the limit as n approaches infinity of n factorial equals the quantity n over e raised to the power of n times the square root of 2 pi n. So what this formula is really asserting is that as our factorials get bigger and bigger, as we take factorials of bigger and bigger numbers, we can approximate that factorial by this amazing formula. So as I said, we're going to use Laplace's method to derive Stirling's formula. But to develop Laplace's method, we first need to consider what's known as the Gaussian integral. This is the integral from negative infinity to positive infinity of the function e to the negative x squared dx. And this integral, of course, is famous because it is the area under the so-called bell curve, and it has wide applications in both probability and statistics. And we're going to use it here as well. So there's our sketch of the function y equals e to the negative x squared. And I just want to note that in addition to its peaked bell curve shape, it, of course, also is symmetric. And at x equals 0, the function equals 1. And now, the integral from negative infinity to positive infinity of this function would be represented by the area under the curve. But one of the most interesting things about this function, y equals e to the negative x squared, is that there's no way to directly compute its antiderivative. So we can't evaluate this integral merely by doing antidifferentiation. We have to use some more clever techniques. And so after struggling in vain to compute the antiderivative of the function y equals e to the negative x squared, and by the way, it's now been proven that it's impossible to compute that antiderivative, mathematicians eventually figured out that they were actually looking at the wrong integral. The problem actually becomes much more workable when we consider the related double integral, the integral from negative infinity to positive infinity of the integral from negative infinity to positive infinity of the function e to the negative quantity x squared plus y squared, close parenthesis, dx dy. Now, it might seem at first blush that computing a double integral is going to be inherently more challenging than computing a single integral, but we're going to see that that's actually not true here. And so the first thing I'm going to do is rewrite this expression as the double integral of the function e to the negative x squared times e to the negative y squared dx dy. I'm just using the rules of exponents there. And then this expression will equal the double integral of, just switching the order of terms here, e to the negative y squared times e to the negative x squared dx dy. Now, for those of you watching who haven't taken a course already in multivariable calculus, don't be intimidated at all by this expression. What we're really doing is performing two integrations. First, we're going to integrate the expression e to the negative y squared times e to the negative x squared dx in terms of x, and when we do that integration, we're going to be treating e to the negative y squared as a constant, and then we're going to integrate that result in terms of y. So in this integral, in this inner integral, the term e to the negative y squared, again, is going to be treated as a constant, which means that I can pull it out in front, and I can rewrite this double integral as the integral from negative infinity to positive infinity of e to the negative y squared times the integral from negative infinity to positive infinity of e to the negative x squared dx. And then again, I'm going to integrate that result in terms of y, so then I'm going to have a dy at the end. Now, when we perform this second integration, the integration from negative infinity to positive infinity of e to the negative y squared times that integral in x, which I've put in parenthesis, dy, when I'm integrating with respect to y, the integral in parenthesis there, which is purely in terms of x, whatever that integral equals, I can also just treat it as a constant because it doesn't have any y terms in it. So I can actually treat it as a factor coming out in front of my y integral. And I can then rewrite the expression as the integral from negative infinity to positive infinity of e to the negative x squared dx, again I'm pulling it out as if it were a constant, times the integral from negative infinity to positive infinity of e to the negative y squared dy. And so what the above analysis shows is that our double integral of a function in two variables, x and y, in this particular instance can actually be broken down into the product of two single integrals of the functions e to the negative x squared and e to the negative y squared. And so now this first term in the product, the integral from negative infinity to positive infinity of e to the negative x squared dx, that, of course, is just our Gaussian integral, and we still don't know what it equals, so let's just call its value capital I. But now if we look at the second term in the product, the integral from negative infinity to positive infinity of e to the negative y squared dy, a moment's thought would indicate that this is actually the same Gaussian integral, just written with a different variable in the expression. But the fact that it's written with a y instead of an x really doesn't change anything. Y is actually just a dummy variable here. So it's also going to evaluate to the same value capital I. So we know that whatever this double integral equals, it's going to evaluate to the value of the Gaussian integral capital I times capital I, or just capital I squared, where once again the value of capital I is equal to the value of the integral from negative infinity to positive infinity of e to the negative x squared dx, a value which is still to be determined. So we've seen that the value of this double integral must equal the value of the Gaussian integral squared. So if I can compute the value of this double integral, I'll be home free. I just take the square root of the result, and then I know what the Gaussian integral equals. And as I said, this double integral is actually much more workable. And the reason for that is that I can convert this double integral in x and y into a double integral in polar coordinates. Right? Whenever we see an expression x squared plus y squared, we should immediately think of the Pythagorean theorem and polar coordinates. So here we have, doing our variable substitution, that x will equal r cosine theta, y will equal r sine theta. And then we'll have x squared plus y squared equals r squared cosine squared theta plus r squared sine squared theta, which equals r squared times the quantity cosine squared theta plus sine squared theta, and by that famous trig identity, cosine squared theta plus sine squared theta equals 1, we have x squared plus y squared, of course, equals r squared. That's the Pythagorean theorem. So x squared plus y squared equals r squared. And now we need to convert our infinitesimal area element dx dy also into polar terms. Well, in Cartesian coordinates, the area element dx dy can be represented by that tiny square, an infinitesimally small square. And in polar coordinates, that area element is represented by the infinitesimal rectangle, whose length is just dr, an infinitesimal increment in r, and whose width is going to be r times d theta. Why not just d theta? Well, the reason is that the width is actually an infinitesimal piece of arc, and we know that the length of a circular arc subtended by a central angle theta is equal to the product of the circle's radius and the angle, which in this instance is d theta. Right? The length of that piece of circular arc doesn't only depend on theta, it also scales with r. So when we convert from Cartesian to polar coordinates, we have that the infinitesimal area element dx dy becomes dr times r d theta, or just r dr d theta. And so now in polar coordinates, our integrand becomes e to the negative r squared times r dr d theta, and our bounds of integration now are in terms of r and theta. So the inner integral is in terms of r, so that will be from r equals 0 to r equals infinity, and the outer integral is in terms of theta. That will be from theta equals 0 to theta equals 2 pi, because we're sweeping out the entire plane now in terms of polar coordinates instead of in terms of x and y. Now, why is writing the double integral in polar coordinates such a great idea? Because it allows us to make the following u substitution. We're going to let u equal r squared. Then we have that du dr equals 2r, or du over 2r equals dr. Then the integrand becomes e to the negative u times r times du over 2r d theta, and the r's cancel. Well, that's kind of awesome, because now I have that this expression equals the integral from 0 to 2 pi of, just pulling out that over 2 factor, 1/2 times the integral from 0 to infinity of e to the negative u du d theta. And so now we can do this integration. This is going to be the integral from 0 to 2 pi of 1/2 times, tackling the inner integral first, negative e to the negative u, evaluated from 0 to infinity, close parenthesis d theta. So this will equal the integral from 0 to 2 pi of 1/2 times, open parenthesis, the limit as m approaches infinity of negative 1 over e to the m minus negative 1 over e to the 0. Now, the limit as m approaches infinity of negative 1 over e to the m goes to 0, and then that double negative there becomes a positive, so it becomes plus 1 over e to the 0, or just plus 1. And so we get 0 plus 1 in parentheses there, and this equals the integral from 0 to 2 pi of 1/2 times 1 d theta. So this integral equals 1/2 times theta from 0 to 2 pi, which equals 1/2 times 2 pi minus 0, which just equals pi. And so by converting to polar coordinates, we found that the double integral actually equals pi. And we know that the value of the double integral equals the value of the Gaussian integral, capital I squared. So capital I squared must equal pi, which therefore implies that the value of the Gaussian integral squared equals pi, and therefore the Gaussian integral, the integral from negative infinity to positive infinity of e to the negative x squared dx, must equal the square root of pi. How cool is that? Well, with that result established, that the value of the Gaussian integral equals the square root of pi, we can now study the family of integrals that are directly related to the Gaussian. So the first property I want to consider is what happens if we shift the Gaussian function over by some amount. So let's consider what that will do to the integral. So we have the integral from negative infinity to positive infinity of the related function e to the negative, open parenthesis, x minus mu, close parenthesis, squared dx. Again, I'm just shifting the Gaussian integral over by some amount mu. And so what the graph of that will look like is that we'll have our bell curve shaped function, but now it will be centered at some value mu instead of centered at 0. And your intuition might tell you that that integral from negative infinity to positive infinity isn't going to change just by shifting. And so let's actually prove that. So we have the following u substitution. We're going to let u equal x minus mu. So du dx equals 1, and du equals dx. And then we have that the integrand is just e to the negative u squared du. And of course this integral again is just the Gaussian integral, writing u in place of x, and so its value equals the square root of pi. So shifting the Gaussian integral by any amount isn't going to change the ultimate result, which is that the integral from negative infinity to positive infinity of that shifted Gaussian still is going to equal the square root of pi. The next property that we want to consider is what would happen if we were to multiply that negative x squared in the integrand, in our exponent, by some positive constant a. Well, when we set a equal to 1, of course, we just recover our usual Gaussian function. But what if we set a equal to 10? Well, you can take out a graphing calculator to confirm this for yourself, but what you'll see is that you still get a bell-shaped type curve, but now it's much more narrow and it still peaks at x equals 0, y equals 1. And then if we made a even larger, for example, if we set a equal to 100 so that we were looking at the function e to the negative 100x squared, that's going to be a very pinched in, narrowly peaked function, but it's still going to have that overall Gaussian shape and attain its maximum at x equals 0. Now to compute what these integrals actually equal, we do the following u substitution. We set u equal to radical a times x. Then we'll have that du equals radical a times dx, because of course radical a is just a constant here, so 1 over radical a du equals dx. Then when we integrate from negative infinity to positive infinity our function e to the negative a x squared dx, we have that this equals the integral of the function e to the negative quantity radical a times x, close parenthesis, squared dx. And so this is going to then equal the integral from negative infinity to positive infinity of e to the negative u squared times 1 over radical a du. I can then pull out that 1 over radical a since it's a constant, so this will equal 1 over radical a times the Gaussian integral, and that's then going to be 1 over radical a times the square root of pi, or more simply put, the square root of pi over a. So I'm going to put a box around that result. Actually, that's going to be useful for us later. Now, for those of you who have been watching the earlier videos in this series, you may recall that we've seen the constant square root of pi before. We saw it in our work on the gamma function. The gamma function, you'll remember, is this incredible function that generalizes the concept of factorials to non-integer inputs. And so we found the very important result that gamma of 1/2 actually equals the square root of pi. And we actually proved this result using the infinite product form of the gamma function, but now because of the work that we've done on the Gaussian, we're going to be able to prove it with the integral form of the gamma function. So please recall the integral definition of the gamma function. We have that gamma of n, where n is a positive real number, equals the integral from 0 to infinity of x to the n minus 1 times e to the negative x dx. We then have that gamma of 1/2 would equal the integral from 0 to infinity of x to the 1/2 minus 1 times e to the negative x dx. So that'll equal the integral from 0 to infinity of e to the negative 1/2 times e to the negative x dx. We'll then make the following u substitution. We'll let u equal radical x. So then du dx equals 1 over 2 times radical x. And therefore dx equals 2 times radical x du. So I'll move those results to the upper right-hand corner of the screen there. U equals radical x, dx equals 2 times radical x du, which I can rewrite as 2u du. Now, of course, that x to the negative 1/2 in the integrand equals 1 over radical x, so I have that gamma of 1/2 equals the integral from 0 to infinity of 1 over radical x times e to the negative x dx. And now making the u substitution, I have that the integrand is going to equal 1 over u times e to the negative u squared times 2u du. So the 1 over u and the u in the integrand there cancel. And I have that gamma of 1/2 equals 2 times the integral from 0 to infinity of e to the negative u squared du. Well, the integral from 0 to infinity of e to the negative u squared du, that's just the integral of 1/2 of the Gaussian, right? The Gaussian goes from negative infinity to positive infinity, and as we said, it's symmetric about the y-axis. So the value of this integral is just going to be half that of the Gaussian integral. So I then have that gamma of 1/2 equals 2 times 1/2 radical pi, and therefore gamma of 1/2 equals radical pi. So now a natural question emerges. Is the fact that gamma of 1/2 equals radical pi just a beautiful coincidence? Or is the Gaussian integral more deeply connected to the gamma function in a more general way? Well, we're going to see that that's in fact the case. So to see that connection, we're now going to consider the gamma function for larger inputs. And really, I'm just trying to give you all a feel for what these graphs look like. So gamma of 4, for example, that's the integral from 0 to infinity of t to the third times e to the negative t dt, and that's what that function looks like. Gamma of 4, of course, is going to be the area under that curve from 0 to infinity. And we know that that area happens to equal 3 factorial, which is 6. The factorial grows super exponentially, and so we're going to find that the graphs of these functions become increasingly sharply peaked. So for example, gamma of 7 is going to be the integral from 0 to infinity of t to the 6th times e to the negative t dt. And this graph isn't even to scale, but this gives you some flavor for what it looks like. It's a very narrow, very sharply peaked graph. And the area under this narrowly peaked graph from 0 to infinity, of course, equals 6 factorial, which is 720. Now you'll notice that gamma of n equals n minus 1 factorial, and that our graphs are actually peaking at that value for n minus 1. So when n equals 4, we saw that the graph of gamma of 4 peaks at x equals 3. When gamma equals 7, we saw that the graph peaks at x equals 6. And now if I were to graph gamma of 100, that's a very narrowly, very sharply peaked graph. I can't do it justice and draw it anywhere near to scale. You'll have to use a graphing calculator to see what it looks like. But this one peaks at x equals 99. And of course, the area under the curve from x equals 0 to infinity is 99 factorial, a huge number. Now, functions like these that have one single global maximum with a narrow, sharp peak to them actually show up all over the place in mathematics. The gamma function is just one example of several. And so we would like to have a way to approximate these integrals, especially for something really large like 99 factorial. Instead of having to multiply 99 numbers together, it would be great if we just had a quick way to get a grip on what this integral is close to approximately. And so the idea behind Laplace's method is to approximate narrow, sharply peaked functions' integrals by something that we understand very well, a narrowly peaked Gaussian function scaled up. So more concretely, if we have a function y equals f of x, which has a global maximum and a narrow, sharp peak at that maximum, then the integral from a to b of f of x dx, where the peak lies between a and b, is approximately equal to the integral from negative infinity to positive infinity of the function e to the a, where a is a positive constant, times g of x dx. And so this integral here that we're using to approximate the integral of f of x is going to be a Gaussian-like integral. Now, some of you watching this might be skeptical or maybe confused at this jump. After all, our Gaussian integral is the integral of the function e to the negative x squared, or allowing for scaling, e to the negative ax squared. I'm now saying that we can replace that with something more general, a function of the type e to the a, where a is again a positive constant, times some function g of x. And it might seem that that function that I'm replacing e to the negative x squared with is just too general to be useful. But now we're going to impose some conditions on g of x, and in so doing, you'll see that we're going to recover an integral that looks very much like a Gaussian. So for starters, the function whose integral we wish to approximate has its peak, its global maximum, at some value for x, which we'll just call c. So we're then going to require that the approximating function e to the a times g of x also must attain its maximum there. This implies that the derivative of e to the a times g of x, evaluated at x equals c, must equal 0. So now performing this differentiation, we'll have that e to the a times g of c, now using the chain rule, times a times g prime of c must equal 0. But e to the a times g of c must always be positive, and therefore a times g prime of c equals 0, and we've already stipulated that a is a positive constant, so this therefore implies that g prime of c must equal 0. Second of all, because e to the a times g of x at x equals c is concave down, that means that the second derivative of e to the a times g of x, evaluated at x equals c, must be negative. So to find that second derivative at x equals c, I take the first derivative of the function, which we've already found equals a times e to the a times g of c times g prime of c, and I differentiate that again using the product rule. So I'll have the first function times the derivative of the second, that's a times e to the a times g of c times g double prime of c, plus the second function times the derivative of the first, so that's going to be g prime of c times the derivative of a times e to the a times g of c. But I already know that g prime of c equals 0, so that whole term must be 0, and it just drops out. And then once again, a is a positive constant here. E to the a times g of c must be positive, and so that therefore implies that g double prime of c must be negative. So I'll bring those two facts to the upper right-hand side of the screen there, that g prime of c must be equal to 0 for this approximating function to have a global maximum at x equals c, and furthermore that g double prime of c must be negative for the function to be concave down there. And now the real magic of Laplace's method happens. We're going to expand g of x as a Taylor series centered at c. So watch what happens when we do this. By Taylor's theorem, we have that g of x equals g of c plus g prime of c times x minus c, quantity to the first, over 1 factorial, plus g double prime of c times x minus c quantity squared over 2 factorial, plus g triple prime of c times x minus c quantity cubed over 3 factorial, plus dot dot dot. But we already know that g prime of c equals 0, so that first order term drops out of the Taylor expansion. The next thing we know is that g double prime of c must be negative, so I'm going to rewrite that term as minus the absolute value of g double prime of c times x minus c squared over 2 factorial. That guarantees that we're going to have a negative quantity there. So near c, e to the a times g of x equals e to the a times, and now here's the Taylor expansion for g of x, g of c minus the absolute value of g double prime of c times the quantity x minus c squared over 2 factorial, plus g triple prime of c times the quantity x minus c cubed over 3 factorial, plus higher order terms. Now remember, in general for Taylor series, the closer our values of x are to c, the better the Taylor series approximation gets. And I just want to observe that if our function y equals e to the a times g of x has a maximum at some point x equals c, then as our parameter a becomes larger, the function e to the a times g of x becomes more sharply peaked around c, which actually helps with our integral approximation because more of the values that actually contribute to the integral, that contribute to the area under the curve, are going to be clustered near c, which is the point where the function is best approximated by the Taylor series. Now, why is it that as we increase our parameter a, the function becomes more sharply peaked around c? Well, in order for our approximating function e to the a times g of x to have a global maximum at x equals c, that implies that the function g of x must also have a maximum there. So in other words, g of c is greater than g of x for all x. And so this means that for x near c, g of x is less than g of c, and then when we actually exponentiate that inequality, e to the g of x must be less than e to the g of c. Then for large a, e to the a times g of x, well, that's really e to the g of x raised to the power of a. So that exponential increase up towards c is going to be very sharp, and then that exponential decrease for x greater than c as it shoots back down, that's also going to be very sharp. So the key idea here is that exponential growth and exponential decay are both very fast processes. So if we multiply g of x by a very large constant a, we're going to see very rapid exponential growth and then very rapid exponential decay around our maximum c. And once again, what that means for our integral approximation is that as a grows large, the only values of x that are going to really contribute to this integral from negative infinity to positive infinity of e to the a times g of x dx are going to be the values of x that are in a shrinking neighborhood centered at c. So we've seen that for a large parameter a, the only values of x that really contribute meaningfully to the integral lie in a small neighborhood around c, which is also where the Taylor series happens to give the best approximation. So those two things work in our favor. And notice something else, that for x near c, those higher order terms like x minus c cubed over 3 factorial or x minus c to the fourth over 4 factorial, if x is close to c, those higher order terms become vanishingly small. So those higher order terms can actually be neglected in the Taylor series approximation because they contribute so little to the ultimate result, and we have that for x near c, g of x is approximately equal to g of c minus the absolute value of g double prime of c times the quantity x minus c squared over 2. That means that e to the a times g of x is approximately equal to e to the a times the truncated Taylor series for g of x, which is g of c minus the absolute value of g double prime of c times x minus c quantity squared over 2. And now we can integrate both sides, so we'll have that the integral from negative infinity to positive infinity of e to the a times g of x dx is approximately equal to the integral from negative infinity to positive infinity of e to the a times our truncated Taylor series dx. And then the right-hand side would become that this equals the integral from negative infinity to positive infinity of e to the a times g of c times e to the negative a times the absolute value of g double prime of c times the quantity x minus c squared over 2 dx. But that first term e to the a times g of c, a is a constant and c is a fixed value, so g of c is also a constant, so I can pull that out from the integral, and I'll have that this equals e to the a times g of c times the integral from negative infinity to positive infinity of the function e to the negative a times the absolute value of g double prime of c times x minus c quantity squared over 2 dx. But our integral e to the negative a times the absolute value of g double prime of c over 2 times x minus c quantity squared, that's just a shifted scaled Gaussian. And so I have that this expression equals our constant out front, e to the a times g of c, and now evaluating the Gaussian integral, this will equal the square root of pi over that scaling factor, so over a times the absolute value of g double prime of c over 2. So simplifying, we can write that this equals e to the a times g of c times the square root of 2 pi over a times the absolute value of g double prime of c. And I'm going to put a box around this result. This is how we can approximate integrals of sharply peaked functions. And we're now going to see how we can apply Laplace's method to the theory of the gamma function and factorial function. So we have from our integral definition of the gamma function that gamma of n equals the integral from 0 to infinity of x to the n minus 1 times e to the negative x dx, and that this equals n minus 1 factorial. Therefore, gamma of n plus 1, which would be the integral from 0 to infinity of x to the n times e to the negative x dx, must equal n factorial. So we've already seen that for large inputs, the gamma function has a sharply peaked global maximum, which makes it a good candidate for approximation by Laplace's method. So I'm going to start by rewriting our integrand x to the n times e to the negative x in a slightly different form. I'm going to write everything in terms of base e, so this will become e to the log of x to the n times e to the negative x, which equals, by the laws of exponents, e to the n log x times e to the negative x, which equals e to the n log x minus x. Then we'll have gamma of n plus 1, which equals n factorial, equals the integral from 0 to infinity of e to the n log x minus x dx. So now we need to find for what value of x does e to the n log x minus x attain its maximum. So this is just a sketch of a possible graph for e to the n log x minus x, and so we're trying to find this value for c. And so to find it, we're going to take the derivative of our function and set the derivative equal to 0. So we're going to differentiate e to the n log x minus x and set that equal to 0. So then we'll have, by the chain rule, that the derivative equals e to the n log x minus x times n over x minus 1. And then we're going to set that derivative equal to 0. But we know that e to the n log x minus x can never equal 0. E to the anything is always going to be a positive number, of course. So that implies then that n over x minus 1 must be the factor equal to 0, which means n must equal x. In other words, this function e to the n log x minus x attains its maximum when x equals n. So now we're going to want to rewrite our function e to the n log x minus x in a form that looks like e to the a times g of x, but I don't see any kind of constant that I can pull out from this expression n log x minus x. And the key step here is to do the following variable substitution. We're going to set x equal to n times t, and then we'll have that dx dt equals n, so dx equals n dt. Setting x equal to nt here, we'll then have that n factorial equals the integral from 0 to infinity of e to the n log nt minus nt times n dt. So the first thing we'll do is we'll just pull out that constant factor n in the n dt. We'll just pull that constant factor n out in front of the integral. And then I'm going to simplify the integrand a little bit. So e to the n log n, that just simplifies to n to the n, and then that will multiply e to the n log t minus nt dt. And so we'll have that n factorial, pulling out that n to the n now, equals n to the n plus 1 times the integral from 0 to infinity of e to the n times the quantity log t minus t, close parenthesis, dt. So finally, our factorial function is in a form where we can use Laplace's method to estimate it. Again, we have n factorial equals n to the n plus 1 times the integral from 0 to infinity of e to the n times the quantity log of t minus t, close parenthesis, dt. And so now, Based on Laplace's method, our value a, our parameter a, is going to be equal to n, and we're going to set g of t equal to the function log t minus t. Well, what else do we need for Laplace's method? We need to find c, the value for t where g of t attains its global maximum. So we have g of t equals log of t minus t, therefore g prime of t equals 1 over t minus 1, and then setting that derivative equal to 0, we'll have 0 equals 1 over t minus 1, therefore t equals 1, which means c equals 1. And then we'll have g of c equals log of 1 minus 1. Well, log of 1 is just 0, so g of c equals negative 1. And then g double prime of t here, we need that to find g double prime of c. G double prime of t would be negative 1 over t squared. So then the absolute value of g double prime of c would just be the absolute value of negative 1 over 1 squared, which equals 1. And now we can use Laplace's method to estimate the integral. So by Laplace's method, we have that n factorial is approximately equal to n to the n plus 1, that's just a leading constant, times, and now here's the estimation of the integral, e to the n times negative 1, times the square root of 2 pi over n times 1, where I'm just substituting into the formula given by Laplace's method the values that we found for a, c, and the absolute value of g double prime of c. So now we can simplify this expression a little bit. I'm going to take that leading term n to the n plus 1, and I'm going to write it as n to the n times n. And then I'm going to pull that n actually inside the radical sign. So that will become radical n squared inside the radical sign. And then we'll have that n factorial is approximately equal to n to the n, and now e to the negative n is 1 over e to the n, so I'll write it as n to the n over e to the n times the square root of 2 pi n squared over n, but of course that exponent in n cancels with the denominator, so I'm left with n factorial is approximately equal to n over e, quantity to the n, times radical 2 pi n. Now we already saw that as our parameter a in the formula for Laplace's method gets larger and larger, the approximation gets better and better, and here a equals n. So asymptotically, this approximation becomes an equality as n approaches infinity. So we can write that the limit as n approaches infinity of n factorial equals the quantity n over e to the n times radical 2 pi n. And this is the very famous and very beautiful Stirling's approximation, or Stirling's formula, which gives us an approximation for large factorials. So hopefully it's clear from this derivation where that factor radical 2 pi n comes from. I think it's less clear in the derivation using the Euler-Maclaurin summation formula. The radical 2 pi n comes from the fact that as n gets larger and larger, the factorial function looks more and more like a narrowly peaked Gaussian. I also want to observe that this formula is actually extremely accurate even for relatively small values of n, which is part of what makes it incredible also. And it's used even today in computational science for computing large factorials, where instead of having to multiply thousands or even millions of numbers together to find a large factorial, we can just multiply a handful of numbers and get a very accurate estimate very quickly. Well, that's it for today's video. I hope you enjoyed it, and if you did, please like or subscribe to my channel. Thanks again.